Welcome everyone. In this video, we'll see what material we'll be covering in the first unit. So I've divided the first unit into 3 chapters, the first one being about tensors, but in a naive way, and then we'll see tensors more formally in the second chapter, which is about manifolds. Then, in one of the 2 books that I recommended for bibliography, there is a space-time from Carroll, and he introduces a little bit of classical field theory, and I thought that it was a good idea to also talk about classical field theory in this course a little, because it's very interesting, and when we know some tools like tensors, it's very fun. So in the first chapter about tensors, we'll learn the basics about index notation, and then we'll see some important objects, which are the Kronecker delta and Levi-Civita. These objects allow us to take dot products and also the cross product between vectors. Then I'll show some examples where this index notation is very useful, which is for deriving vector calculus formulas that you might encounter. If you have seen classical electrodynamics from, well, just Introduction to Electrodynamics by Griffiths, I'm sure that if you are in college you may know that book. There's like a page where you have some vector identities, like for derivatives, for the gradient, the curl, and we can derive all those very easily with index notation. Then we'll see a little about rotations, and we'll see what are vectors, that here in general relativity vectors are called tangent vectors, and we'll see why. And also the cotangent vectors, which are also what in algebra at the first college and the first year of college, cotangent vectors are what called dual vectors in algebra. Then we'll see finally what are tensors, but as I said, in an introductory way. And then we'll see that we can represent some tensors as matrices. Then we'll see a very important concept in relativity, which is a metric. The metric is what allows us like to measure the curvature of the space. And we'll finish the first chapter with symmetric and antisymmetric tensors. Then in the second chapter, we'll define formally what's a manifold, and we'll see vectors and tensors again in a more formal way. And then we'll talk about some properties about tensors, that some may have what is called tensor densities. And we'll also talk about differential forms and dual tensors. And lastly, the classical field theory that I mentioned before, that I included in this unit, will derive Lagrange equations, but instead for some coordinates of an object, we'll derive the Lagrange equations for a field. It's really the same procedure, so it's not going to be tough if you've already seen Lagrangian dynamics. Then we'll see how we can derive Maxwell's equations from a Lagrangian. And finally, we'll see that if we introduce a scalar field in the Lagrange equations, we obtain the Klein-Gordon equation. So I hope you enjoyed this course and this first unit, and see you in the first lesson.